Hello everyone, welcome to IndoML session 2, and it is on machine learning in NLP. We have 3 very interesting talks from our esteemed speakers. Every talk will be 40 minutes followed by 5 minutes question answering. The attendees are requested to post their questions in the Q&A box, and I will direct them to the speaker one by one after their talk. And with this, let me welcome and introduce our first speaker, Professor Ido Dagan. Ido Dagan is currently a professor at the Department of Computer Science at Bar Ilan University, Israel. He is also the founder of Natural Language Processing Lab at Bar Ilan and a founder and head of the nationally funded Bar Ilan University Data Science Institute. He is a fellow of the Association of Computational Linguists. He was the president of ACL in 2010, and he led the establishment of the prestigious Tactile Journal. Today, he will be presenting his talk titled Novel Data for Modeling Textual Information, Decomposition, Multitext, and Interaction. Now over to you, Ido.
Thank you very much. Thank you, Vitisha, for the introduction, and I would like to thank the organizers of the event for inviting me to speak here. This talk would fall under the, within the theme of IndoML, the talk would fall under the data for AI theme. And as the title can suggest, I'm within the NLP community, and I would like to talk about novel types of data that we found, and at my group, we found as relevant and useful for advancing NLP research within the scope of AI. Before starting, I'd like to thank many students, the group of students involved in the projects that I will be describing, and many collaborators from external groups. So to give some context, I'd like to refer to typical use of data in NLP, natural language processing. Generally, there are 2 prominent types of data that have been used in NLP. The first is representing language structure. So there's been a lot of data, many data sets created to represent language structure, mostly following some linguistic theory. And we all know that there are data sets annotated with part-of-speech information or syntactic trees, some semantic annotations, discourse annotations, and so on. And traditionally, these types of data sets were used to train models that can generate such language structures. So over syntactic parsing data, you would train a syntactic parser. Over semantic row labeler, you would train semantic row labeling, some semantic analysis. And the output of these models that could generate language structures or could automatically annotate text with language structures would be in turn used as intermediate representations in n-task models. That was the typical approach. On the other hand, there's another type of data sets that capture n-tasks applications in NLP, like question answering, information extraction, summarization, translation, and so on. And these data sets, like data sets of questions and their gold standard answers, were used to train task-specific models or application-specific models that would perform the end task. So this used to be the state of data in NLP. Now, in this context, it's worth examining kind of the recent trends with respect to explicit versus implicit structures in NLP. So up to the burst of deep learning models, and we had kind of more feature-based models or other structured prediction models, a common practice was to first use models trained to extract particular NLP structures, language structures like parsing or semantic row labeling, name entity recognition, and so on. to extract those as features from the text, and then feed those into some kind of learning models. But more recently, when neural models evolved and became popular, we also have the end-to-end paradigm, right? Under which you just feed in raw text into your model, and this model implicitly somehow, I mean, this is just kind of figuratively, is expected to represent internally some syntactic structure or semantic structure, but this is all completely implicit, opaque, and not under our control. And then we just have the internal model that would train on the end task directly. So from that perspective, under the pure E2E paradigm, the first type of data is not needed anymore, and we are only using the second type of data. But then the question comes up whether such implicit representations are sufficient. And there's a lot of evidence that suggests that at least in certain situations, it is better to still keep using intermediate structures, and many works indeed do not perform in an end-to-end manner, but others show that some intermediate language structures that we can generate explicitly can improve performance. And they also have some additional kind of benefits that they allow us for deeper understanding of the phenomena we're dealing with, better portability across domains, because end-to-end training or fine-tuning tends to be quite less transferable. They give us some interpretability and control over the end-stream task. So if we believe that some structures should be used, the questions come up, which structures we should use. And this leads me to kind of the core of my presentation, in which I'm going to talk about three novel data types. In fact, with respect to the introduction I just gave, the first two are relevant. And I'll focus mostly about the first. This suggests that we can develop some data sets and then train on them corresponding models that would capture information structure in text. And this would be both feasible and also effective for downstream use. But there's a twist here. Rather than suggesting to use some traditional semantics representations, I will be proposing to use representations that are built on natural language question answer pairs. So it's going to be some kind of semi-structured representations. And I'll spend most of the time on this one. Then the next type of data I would like to promote is data that models or captures cross-text information relations. That would be the second part. And these two together kind of suggest that applications both in the single text regime or in multi-text regime could benefit for such types of representations. Then at the end, very briefly, depending on time, I would like to refer to another completely different type of data, and that's the type of data of human interaction sessions with interactive NLP applications, which is something we don't have that much, and I think we should have much more. So let me start with the first part, modeling text information structure, particularly as natural question answer pairs. So as I just motivated, often people find that still using some explicit structures that capture language structure can be useful. This is an example for a line of works on text summarization that used AMR, abstract meaning representation, which is a formal representation, and showed benefits for summarization. More recently, if I'd like to talk about more modern approaches, just at last NACL, both these papers were presented at NACL, at recent NACL, that showed benefit of information graphs, something that looks like illustrated here, that are produced by open information extraction tuples from which you build some graphs, and they've shown that such graphs improve summarization, both to improve faithfulness as well as in multi-document summarization set. So we've seen that we've had different types of structures being used to improve in this example, summarization. Now, if we look deeper at these types of structures, particularly at structures like AMR, the first type I mentioned, which is a typical formal semantic representation, such semantic representations like AMR or others, some semantic dependencies, they rely on some pre-specified relation concepts or types, like having a lexicon of verb senses, having a repository of semantic roles, in this case, semantic roles coming from PropBank that have been used, for example, in AMR and also in other representations. Now, when we base some representation on some kind of a linguistically motivated representation that comes with a predefined schema, there are some consequences. To start with, if we have different formalisms, they would have different schemas, different inventories of roles, senses, etc. Two typical examples are Framenet and PropBank that have different, both deal with semantic roles, but have different role inventories and formalizations. A second consequence of having such a formal schema-based approach is that it requires fairly complex expert annotation. You must really require people with understanding of linguistics or at least natural language processing, and guidelines tend to be very, very heavy, very long, often dozens of pages. And the thirdly, these structures are often less understood by researchers and developers that would like to leverage such structures in downstream use. And these kind of consequences, in a sense, hinder the potential of explicit representations. And I think this is one of the reasons why formal semantic representations are not that common. But there is an alternative, and people have been using an alternative. The two recent examples I've mentioned before from NACL this year, were relying on open information extraction. Open information extraction, as at least the NLP people in the audience know, take a sentence, focus on a predicate like born here, and extract a tuple where the predicate is usually the second argument, subject of the sentence is the first, and then the rest will be, the other arguments will appear in the remaining tuple. And the advantage of such tuples is that they are very simple. The elements are actually natural language fragments, so it's not fully formalized. And these have been popular for their simplicity in use both in research and in industry. But still, OpenAI, traditional OpenAI has some limitations, particularly if you look at another paraphrase of the same sentence. Obama was born in 1961 in Hawaii, just changing the order of arguments, then the representation would change, which is of course undesirable. So the argument role is left undefined, and furthermore, the position becomes inconsistent. So we were looking more deeply into another proposal, which also falls under the semi-structured approaches, which is called QA-SRL, QA-driven semantic role labeling. And here, looking again at the same sentence, instead of just extracting the arguments, Obama, Hawaii, 1961, each of them will be accompanied by a suitable question. So to create such semantic role labeling representation, we will generate a question like who was born and answer it by Obama. And this would identify that Obama answers kind of the who, the semantic role. Similarly, Hawaii answers the where, and 1961 answers the when. Okay, so now we have kind of three role labels, but they are not fully formal. They are just natural language questions, but they pretty much give us a lot of information about the type of semantic relation between the predicate and the arguments. And this we found to be a very appealing approach. But then looking a bit more deeply into this representation, we figured out that, in fact, it's not just semantic role labeling. It can be perceived as a way to represent the information in this sentence, right? If you read these three question-answer pairs, who was born, Obama, where, in Hawaii, when, 1961, I gave you exactly the same information as you would get if you would read the original sentence, Obama was born in Hawaii in 1961. So in a sense, these three question answers may become a representation of the sentence, okay? But just having QSRL, just having semantic role for verbs doesn't capture all the information. That's why we extend it in something we call a QA-SEM, where our goal is to transfer the full text into a set of question answers. So just to see how rich this representation I'll show the directions in which we are expanding QSRL to become a full-fledged QA-SEM paradigm. So look at this can read this sentence, right? It's saying something about some trials about car batteries. And we can apply QSRL, the traditional work. I didn't mention it, but QSRL came from the UW group, Luke Zettelmeier group, started in 2015, and added some subsequent work at 2018. And this is already work at my group that we extended further the formalism or the data annotation scheme. So if we apply this available QSRL that also has a readily available parser, we will get these two questions for the first verb, last, and these two questions for the second verb, held. And they pretty much capture basic roles that appear in this sentence and are related to the corresponding two predicates. At this point, I would just like to point out, for instance, if we look at held, we see here that public release will not be held on the planned date. These are the two arguments captured, and these are also syntactic arguments of the verb held. But in fact, when you look at semantic relations, many of them may be implicit, and it's worth spending a minute on the implicit aspect, because some semantic arguments may not be related syntactically to the predicate. Consider this sentence: I met John while he was walking in the park. Then in the park is a location syntactically connected to the walking. So we can have a question: where did someone walk? In the park. And that's an explicit argument because it's syntactically connected. But if I ask, where did someone meet someone? It's obvious that the meeting was also in the park, right? Because I met him while he was walking. So the meeting was in the park. But this becomes an implicit argument that will not be captured by syntactic analysis, yet it is captured by annotators. So the nice thing about question and answers is that it becomes very natural for annotators to capture also implicit relationships. They are not aware of the syntax, they just communicate to us or capture in their annotation what they understand from the text. And this may be confronted with another syntactically similar sentence that will not have this indirect or implicit argument. So that's about verbs. But again, if we look at the question answers about the verb, this still doesn't convey all the sentence information. We have more information, more statements, more propositions captured in this sentence. For example, some propositions or some information are captured through nominalizations, verbs used in the nominal forms. Like we have here trials, right? We had successful road trials. We may ask how was something trialed? And so would be successful. That would be the manner argument. But we can also ask what was trialed, and here we get another implicit argument that, in fact, you can understand from this sentence that the giant car battery is the answer to the question what was trialed. So like the theme of the trial, and so on. Also for the argument release, the nominalization release also has its own argument. So we may also capture additional propositions. All these are statements expressed in this sentence that are captured through nominalization. Noun compounds may reflect additional statements or propositions. 300-mile mark says that this mark was of 300 miles. Adjectives may say that the release was public. And similarly for other types of noun-centered relations. And finally, it's worth also noting that statements or information statements expressed in a sentence may be expressed through discourse, not just through individual predicates. If you look at these two sentences, there's actually some assertion that's saying that these successful road trials were, that despite that the road trials were successful, the battery itself didn't last beyond 300 miles. So there's some kind of despite of relation, some kind of conditional relation. And similarly, there's some discourse relation between the two sentences. So these also can be captured by question-answer pairs. So altogether, if we do annotation properly, we may be able to transform the text to a set of questions and answers, a larger set of questions and answers, which elicit or the statements or the information for different types of constructions in the sentence, and pretty much convey the entire information. So again, once again, if you read all these question-answer pairs, you would get back the entire information captured in this sentence. And the nice thing about it is that questions, we leverage here questions that are the natural mechanism to tease information parts apart. So if we would build such data sets, we will actually be able to capture how humans, what kind of information humans capture in a text and represent that in a more explicit manner, okay? So if we compare such an approach with the question-answer pairs to a formal approach, we can see that the question-answer approach, this semi-structured approach, may have multiple benefits. On one hand, the representation is explicit. We did decompose our information, so it's explainable. I can explain on which pieces of information I relied. It's controllable. For instance, if I want to generate a summary, like in the other works I mentioned, I can choose which information pieces, which question-answer pairs to include in my summary. I may want to include the fact that the mark was of 300 miles, but maybe I will skip the fact it was successful. So these are the benefits that I get of the type of having some explicit representation. On the other hand, these are NL-based representations. They are not fully formalized. Therefore, they are first easier to annotate, as I mentioned, that I'm going to illustrate in a couple of minutes. But they are also embeddable. If 10 years ago we didn't know what to do more formal, how to operate directly over natural language structures, now we can take these question-answer pairs and use language models, pre-trained language models, embed them, and then compare language answer pairs, confront them, and make various inferences over them. So overall, this suggests that these kind of question-answer-based representation can be a midway between fully structures and completely latent meaning representation that would, on one hand, would be amenable for the deep learning technologies we have nowadays, but on the other hand, would also give us some control like explicit structures. So that's what we'd like to get, but then the questions from a data perspective, data for AI, is how do we collect such data? And our current efforts are to collect such QA separately for different prominent predication types like those you see here, and these will be the slides I'll show next, a few slides I'll show next. But I would just mention that we also did some attempt back in 2018 where we just let people intuitively generate questions without much guidance, without any guidance actually. And this is in a sense even more kind of flexible. But the problem was that annotators didn't perform sufficiently well. They didn't provide sufficient coverage with respect to the questions, didn't yield some sufficient consistency. So it was quite hard to get something like that, of that scope, just from letting people freely ask questions about the sentence. They would miss many of the relevant questions that they do perceive, but they don't notice when being asked to annotate. Therefore, we take this approach of having specific efforts which guide the annotator how to ask the question. So let me just illustrate that a little bit. So this is the annotation interface developed in this work from UW by Fitzgerald and Julian Michael. These were the lead authors, which basically is based on some grammar, some kind of finite state grammar for this possible structure of sentences to be asked about verbs. And then there is an autocomplete mechanism that guides the annotator to ask the right question. So like if here there's something that appeared and we'd like to know what appeared and get the perpetrators as the answer, the annotator would start what did, and then would have some completion. What didn't someone appear to do? What did appear, etc., and would choose the correct completion. So this would guide annotators to make more comprehensive annotation while still being very, very intuitive to use by just non-expert annotators. For the nominalization that I mentioned, we have something very similar because, as we've seen, we can have a sentence like Thomas has proved something, but on the other hand, we might use a nominalization that Thomas provided proofs, and we still get the same set of question and answers. There's another subtle points that comes up here is that actually some verbal nominalizations like organization are not always used in the verbal sense, and then we should avoid asking such questions. Then they don't predicate like a verb does. And accordingly, we have an annotation interface that to a large extent follows the same one, with the autocomplete. Like here, some discussions with Malala, we can add who is discussing something with someone, we, because we are the discussing, and with whom, who it's with Malala, and so on. And there's an additional question, whether this nominalization appears at all in a verbal kind of usage that makes sense to us with the answers. And again, this is something that non-expert annotators can do, and this is based on, here's the reference, it's a paper we had at Coding 2020. We are now, this is what I'm describing now, is what I'm saying now, is ongoing work where we may have predications over nouns that are not derived from a verbal form like president. And here we have a set of templates that guide the annotator to ask relevant questions about president, like which entity organization does the president belong to? And the answer would be Ford, and what kind of president? So it's vice president, and so on. And this would allow annotators, again, very naturally to annotate noun-centered relations. And finally, also for discourse, as we've seen before, we see here another example where here we have executions were sparked by lawmakers that were requesting action to curb rising crime rates. So we see that what is the reason for requesting action? It's the curbing, and that's what the result is. And again, we have similar interfaces that showing some sentence, like here, that has two propositions, one centered around shown and the other centered around became, triggers the annotator to ask various kinds of discourse-related questions like before what, despite what, except when, what is an alternative to. These are typical informational propositions that are expressed as discourse relations, and we can solicit those as well from annotators. And here you see another example where there is no discourse marker. We just have two clauses adjacent with a comma separating them, but still the question can elicit from users the proper assertion about the relationship between these two clauses, or between these two statements. And we can see here that the annotator can ask despite what, despite he become interested in religious thought, and the answer would be despite not having shown interest in religion before. So quite intuitive interface, again, non-expert interface allows us to extract informational discourse relations that assert additional information within. And finally, for these type of questions, we would like also to extract relations across texts, across sentences. Until now, I only presented mechanisms for extracting the information from a single sentence, so getting a QA representation for a single sentence, but we would like to eventually get a representation for a full text, including cross-sentence statements or propositions. And as you see here, we have here one sentence talking about 1 million prize, and only the second sentence said that Fisher won that prize. So the argument of the agent argument of the winning is actually another sentence. And we would like to somehow guide annotators to ask questions for which the answer appears in different sentences. Now, this becomes more difficult because the search space for the annotator is much larger. And for that, we've made a first step in work that tries to generate questions regardless of the answer. So even if the model doesn't spot an answer or doesn't see an answer in the same sentence, it would generate all possible questions about the predicate one that would guide the annotator to give such questions. And this work just appeared in EMNLP, it's this paper that shows how, given a predicate, we can generate questions about all possible questions for the predicate. And next step, we would like to use that for as a basis for cross-sentence annotation by guiding the annotators with which questions to ask, and then look for the answer also across sentence boundaries. So doing this kind of annotation that I've just presented is feasible, as I mentioned all along, as I claimed all along, for non-experts, and we have a lot of experience with that. But still, it's a bit more difficult than just, and more demanding than just asking people, let's say, to label documents with topics, or to even, let's say, doing probably named entity span, marking name entities. So what we found that if you just try to do the kind of annotations using the interfaces I've shown, to do crowdsourcing in the wild, just open an Amazon Mechanical Turk or using another service a task, and let annotators do that, you don't get sufficiently good quality. That's why we developed this methodology that we published at ACL 2020, and we call controlled crowdsourcing, where we go through several phases. Well, first, we recruit some suitable workers based on some trap tasks. We go through some training sessions in which we give them individual feedback, maybe investing half an hour to an hour in each annotator through direct kind of correspondence. And then eventually we may apply multiple annotators and perform the actual annotation. And this process, we found, keeping good annotators, training them a little bit properly, yields high agreement and high agreement with expert annotation, indicating high quality annotation. These are the data collection projects that we've been going through, trying to really be able to create data sets that translate a text to a set of question answers in order to later train models that can do the same task automatically. And indeed, we have trained some models, and this is just an example for evaluation around the QA norm data set, and also regarding QSRL, where we managed to build some parsers that generate questions and answers for verbs and for nominalizations. And what we've shown in an extrinsic evaluation, that if you further pre-train BERT on these question-answer pairs, you actually get improved performance. I won't go over the numbers here, but you can see that you get improved performance relative to just using vanilla BERT on semantic tasks that seem to require predicate argument structures. And training BERT, further pre-training BERT on this type of systematic question-answer pairs that elicit predicate argument structure perform better than if you just train it on some squad or as an example for just like an arbitrary downstream task question answer data set that doesn't cover the semantics of the data in a systematic way as the approach that I've just shown. And just to mention, we are now working on additional extrinsic evaluations where we try to use the QA representation for summarization, for checking faithfulness, for sentence fusion, and more. So this is an ongoing process, but the phase that is close to completion, is still ongoing, but near completion, is the data collection. And we believe that this really provides very effective data for downstream semantic tasks that is very naturally possible to integrate within typical language model-based architectures. So to sum up on this first part, we've seen a representation that is natural language-based, easy to annotate, and help us to capture the information that humans understand in text. It's amenable for embedding because it's NL-based. On the other hand, as I mentioned before, it's controllable, it's explainable, and it can be a midway between traditional semantic representations and fully opaque representation within neural models, and can provide, but still kind of down the road, to show that it provides more broadly generic infrastructure that can benefit downstream tasks. So this wraps up the first part of my talk. The second is modeling cross-text information relations. So in the first part, I was aiming to develop a scheme that would allow us to elicit or to decompose the information in a single text. But then in many cases, we are interested in multiple texts, not in just a single one, like multi-domain summarization, multi-op QA, knowledge-based population, and many more. In many cases, the interesting information we are we are up to is scattered across multiple texts, and we somehow need to model that information. And more broadly, we could think of multi-text comprehension as a fundamental challenge. Testing models for their understanding of language should require not only understanding a single text, but also being able to look at multiple texts together and somehow jointly comprehend them. So just to illustrate what's the kind of at least one main difference between having a single text and multiple text, is that when we have a single text, we can view what we are trying to do as trying to find certain relations within this text, like semantic roles or coreference resolution. And overall, we can see semantic analysis of a single text as a set of links, as well as some types within the single text. But then when we have multiple texts, we become interested actually in relations across these texts. So maybe the most basic type of relation would be matching. If we have multiple texts, I mean, if the two texts are discussed completely different topics, then there's no relationship between them, and then it's not interesting. The interesting aspects become when the two texts are related and having some related or overlapping information. So one relation we'd like to find is matching, is matching between text pieces. Another one is to find complementary information. For instance, here in the rose garden, we have multiple types of information. See, by the way, I might have kind of miscalculated my time here, but I'll rush a little bit more in this part. So we would somehow like to capture this type of relationships. And how would we do that? So to start with, if we have like 4 texts here, the classic way of modeling cross-text information is modeling cross-document coreference. These would mark or identify different mentions in different texts that all relate to the same entity or event, like President Obama, or the naming here, naming, let's say, here, and the approached here, both refer to the same naming event. And we've done some work on cross-document coreference, extended it with several data sets. You're welcome later to look at these references, but I would like to talk now briefly about extending these works to a broader level, a proposition level. And again, because I just see that I had some mismatch here with calculating the time, so I'll skip this first work. I just point at the paper, which suggests to align work not just for individual elements, but for complete propositions. Just as an illustration, identifying that this proposition about Prime Minister Hun Sen is the same as the red proposition here, and similarly doing for other proposition spans. So it's kind of decomposing the matches between different texts to a substantial level that goes into individual statements, individual propositions centered around the predicate. But I'm going to skip this one, again, for this kind of time shortage. And I'd like just to point out at another work that tries to bridge information or link information between the texts, between 2 different texts, using the same QA approach that I've shown in the first part. And the idea here is that if you have a single sentence presented with its QASR representation, look at this sentence about an earthquake rattling certain regions, we can decompose this sentence to these 3 question-answer pairs. Okay, the first one refers to the agent of the rattling, and the second to 2 arguments of the location. If we have 2 related sentences talking about the same earthquake, we can try and represent each of them with its own set of questions. This is the one for question A, and this is a set of questions for question B. Now we can again turn to annotators, because this is a very natural and intuitive representation, and ask them to align those. So it is quite feasible to get from, again, non-expert annotators an alignment that the first 2 question answers are aligned and refer to the same information, and that the second question answer pair for sentence B refers to the same second and third question answer pairs in the first sentence. So there is a co-reference here because both of them refer to the location. And being able to do that, we could collect a data set with high inter-annotator agreement. And we've also seen that we can align much more information across the text than can be done if you just do element level as in traditional cross-document reference. And we've also seen that doing that is helpful for downstream tasks. In this case, we applied it to the sentence fusion task where you have two sentences and need to generate a summary. So the typical way to approach this task nowadays is fit these two sentences into a seek-to-seek model, but specifically we were working with BART. And BART will generate a target sentence. What we tried as well is to inform BART with the alignments produced by our QA alignment model, the model that was trained on the data set that we created. And that would mark for BART that this order and this ordered are aligned, or this mediation are aligned. And this yielded much better few sentences. With the baseline, BART had a strong tendency to just pick only one of the sentences as the output, while with our alignment information provided, BART, in 50% more cases, actually fused information coming from both sentences, which is our end task. So the takeout is that as we want to have explicit presentations and data sets that represent the internal semantic structure or information structure within a single text, as I've illustrated with the as I've promoted with the QA approach, we also want to bridge across texts in the way that I just mentioned. And this can also be done using question-answer representations. And we could solicit from humans not only how they understand the meaning of a single text, but also how they relate the information across text. And again, this can be useful in downstream tasks, but it's only initial steps and there's a lot to explore. Abidish, I assume we are running out of time, right?
Yeah, if you want to take, you can take a couple of more minutes. Yeah.
Okay, so maybe just a couple minutes. I mean, the last part was, I mean, originally I intended to make it short, but I'll make it even shorter. So the main part of my talk was what I described so far, trying to create explicit representations of meaning that will be useful for single and multi-text applications. I'd like just to make a teaser pointing at another line of work, which is about interactive NLP applications. And we know, and just the elevator pitch here is that most NLP applications that we have nowadays are static. And when we develop such applications, they are in batch mode. You just have some data set that simulates a task like summarization. You get your input text or multiple text, and you need to generate a summary. However, in many NLP applications, it seems that interaction could help for two main reasons. For one, you might be adjusting dynamically to the user needs, create better summaries, maybe define better information extraction classes. On the other hand, it may also improve quality. We all know that even with the greatest and latest models we have, performance is not always so good, especially in challenging settings. So users may help the machine to obtain better results. And for that, we need interactive systems that are still not that popular. And I'll just illustrate, I'll just show here like a paper we published again at last Knuckle that shows us a scheme for interactive summarization where when you want to present, let's say, a summary of 25 articles about global warming, you would first get the standard static summaries, an initial summary, but along with it, you get suggested queries about additional information that you might explore. So suppose I'm interested in learning more about carbon dioxide in the context of global warming, I can click it and get more information. Or I might see that it also talk about greenhouse gases, and I might ask about that and get more information about greenhouse gases. So this way, I can explore much more dynamically, much more effectively the information than getting in a single text. than getting, sorry, in a single summary or in a static setting. So what and I'll skip this one. What I'm suggesting here is that we should be able to evaluate such interactive settings, and that's in this paper. You're welcome to look. But more often, more importantly for our context, is that we should start collecting data sets of interactive user sessions with Nlp applications, interactive Nlp applications. And again, this can be done using a controlled crowdsourcing manner similar to what we've been doing in the first part. So I would encourage you to have a look at this paper and try to get from that inspiration also for other NLP tasks. As said, this is only a teaser. So here I'd like to conclude, maybe just show quickly my acknowledgement slide and open for questions. So maybe I'll just the conclusion slide for the questions.
Thank you very much for your talk. Yeah, I think we are running out of time, but we can take a couple of questions. So yeah, so first I will ask the panelists if they have any questions. People can post it to the Q&A chat box if they have any. Yeah.
So can I ask?
Yeah, sure.
So thank you, Professor, for this nice talk. So in this interactive summarizations, from where are you getting those topics? Are those predefined, or you are discovering those topics?
Thank you. Yeah, that's a relevant question. So in this, I mean, the goal of this research step was basically to try and extend the framework of static summarization, particularly multi-document summarization, where the input is a set of 25, a cluster of documents in a topic, and the output is a single static summary. This is a well-established task for, a couple of decades now. So we followed the same setting and extended it to the interactive setting. So actually we use the same data sets, DAC and text data sets, if you're familiar with them, used for static multi-document summarization, and we leverage them for the interactive setting. Of course, it will be very interesting maybe to expand the interactive setting also for dynamic data collection. So you can assume that during an interactive summarization session, a system might conduct additional searches, let's say, and bring in more documents. But the first phase we presented this year follows the standard setting, but extend the summary generation to interactive setting. The data remains the same as in the static setting.
Thank you.
We have one question. Can a generative model generate these questions?
Yes. So as I mentioned, for QSRL, QA norm, the nominalization, and QA discourse, there are already parsing models that generate the questions. In fact, we are now working with an architecture that uses a seek-to-seek approach in order to make a comprehensive parser for all of them. So the answer is that we have initial results showing that the seek-to-seek approach is promising. And for QSRL specifically, there is a downloadable parser. So if you would like to work firstly with a verb kind of question answer pairs, just look at the 218 papers in my slides, and you can download an effective, high quality parser for verbs on a seek-to-seek approach.
So we have another question, but for the sake of time, probably we can answer that offline. Yeah.
So people are welcome to send me email. I'll be happy.
Sure.
Happy to answer because I don't have QA interface here.
Yeah.
Okay. Thank you.
Thank you very much for this talk.